remote class, and we will continue in this way for, as far as we know today, for the next 2 weeks, and we will see later what happens. So at the moment, I would like also to confirm that on Wednesday, which is 17, there will be no class. So this is cancelled and will be recovered at the end of the course, that we have some spare date available. Because I'm okay for different reasons. Now we are talking about the one-dimensional flows with different driving potentials. We have seen everything together so far, and in particular we have seen that we can write the governing equations as a matrix multiplying our let's say derivatives or differentials of pressure, Mach number, and temperature that we have selected as the pair of state variables together with kinetic variables that are necessary to solve the problem. And we have seen that this is governed by different, we have called source terms or driving related to our driving potentials, which have been referred to as SC, SM, SE. This matrix A, I will report it here, is just a function of the Mach number. And that's these coefficients, 1, 1, 2 delta m squared. Here delta is gamma plus minus 1/2. 1, 1/2, and 1/2. Well, from this, what we have seen is that we like to solve for dp dm dt, so we proceeded to invert this matrix A. And let's recall also that our source terms are related to the driving potential, area change, and mass addition here for the first source term related to continuity equation. The second, so C means continuity, Sm is related to friction and mass addition. Where we see that these terms related to mass addition also depends on the direction, on the amount of velocity, or better of momentum that we give in the x direction. And finally, we have SE for the energy equation that we have seen related to the exchange of heat and work, and again to mass addition depending on the enthalpy content of the added mass. So we solved for dp dm m dt t for this vector by calculating our inverse matrix. And at this point, we can also identify a vector of unknowns, which are for us P and T. Let's say that this is the transpose of this vector. And so from this, we can write that our system of the ordinary differential equation would be something like y prime is a function, it's a vector also, of course, of our unknown x and our set of unknowns y. So the first derivative means derivative with respect to x. So this f can be expressed in this way. This is a possible way to keep it, let's say, relatively compact. These are 0. And then we have that PMT will be present on the right-hand side. Sorry, here it's better to use here just A. And let's say S is this vector here. So we can write this set of governing equation, and in principle we can solve it. The problem that we found is that to make this inversion and pass from the governing equation here to this form here in general, what happens is that, of course, we have to invert, and we have this determinant of A, which is equal to m squared minus 1 over gamma m squared 1 plus delta m squared, which has a singular point at m equal to 1. So the singular point means that the governing equation cannot be expressed in our canonical form, and that this is a critical condition, whose meaning probably is what we would like also to deepen here. So we consider that these results come from a rearrangement of equation from a mathematical point of view, but as an important meaning that is the special case of Mach number equal to 1. Actually, what happens from a mathematical point of view is that we have a singular matrix, so we cannot invert the system of equation, and we have no solution for this set of differential equation unless we have that one of the equation is a linear combination of the others, because in that case we have a 0 over 0 form, so that we have, let's say, something which is not determined, and actually we can have a number of possible solutions. So we can see that we have no solution if this is not a linear combination of one equation is not a linear combination of the others, or we have infinite solution if the latter is true. So if we have a linear combination, and to have a linear combination means that not only the left-hand side, which can be expressed as a linear combination of the other because we have this 0 determinant, but also the source term correspond to the same linear combination. So the requirement is that right-hand side should also be the same linear combination as the left-hand side of our starting point, our system of starting point as the system of governing equation. So this must happen when Mach number is equal to 1. So we can look to this matrix when m is equal to 1, and we see that this is here as this expression 1, 1, 2 delta 1 plus delta, and 1 is 1 half, 1 half, 1. So we can find in this way the coefficient for the linear combination, multiplying each equation by one, a different coefficient, and then assuming one given value for one of them, and the other will be obtained as a consequence. So the first equation will be a plus b over gamma plus 0c. I'm looking, so vertically this must be, I have to find the coefficient. So the first equation is the first line multiplied by a, the second equation is the second line multiplied by b, that equation, governing equation, is the third line multiplied by c, and I have to get the coefficient are all at the same linear combination. So I have to make a plus b over gamma going vertically plus 0 by c must be equal to 0, as well as a plus b, second vertical column, a plus b minus 1/2 c. No, I'm not going vertically. A plus b plus 2 delta 1 plus delta c equal to 0, and minus 1/2 a plus 1/2 b plus c is equal to 0. So if we take 1, so of course this is an homogeneous system, I can find a solution assigning, for instance, a equal to 1, and I see from the first equation that b must be equal to gamma, and from, for instance, the third equation, I can find that c must be equal to minus 1/2 gamma plus 1. So it means that, looking now at right-hand side, the set of equations is a linear combination if for the left-hand side there is valid the following relation, which is minus 1 as c plus b, that is gamma, as m, then c minus 1/2 gamma plus 1 as e equal to 0. So this is the critical condition for the right-hand side, and if this is condition is satisfied, we can consider also a system of equation which is defined at unit Mach number. If this is not the case, of course, it means that such a condition cannot be satisfied by the governing equation, that I mean the condition Mach number equal to 1. So let's make now some further consideration of our system of governing equation. We have obtained solutions in terms, not solutions, expressions or dependencies of the different quantities of interest, pressure, temperature, and Mach number. We have seen expressions as a function of the Mach number and of our source terms. The same can be done also for other quantities that can be of interest. So we start from something related to P, M, and T, but for instance, we may be interested to changes of entropy. So if we recall that from the thermodynamics laws, we have dH is equal to TdS plus dP over rho. So where S and H are specific value with respect to mass in this expression, we can also rearrange this, dividing everything by T and recalling that dH is Cp dt for our a thermally perfect gas. So we can also identify a relation for the entropy as a function of temperature and pressure that we have already expressed as a function of the Mach number. So what we can, I'm intending the differential part of all these quantities. So we can say that ds over r will be equal to, I'm dividing by RT, so Cp is gamma r over gamma minus 1. And so we see that here, instead of dH, we have gamma over gamma minus 1, and RT will be a denominator, and so it will be gamma over gamma minus 1 dt over t. Then we the second term is considered, we bring it on the left hand side of this equation. That means right hand side here is dp over rho RT, which is exactly P. And so it will be minus dP over P. So if I take the expressions that we have shown last time, and the T over T and the P over P as function of M, I obtain, let's say, something that will be yes over R. We put together something which is function of M squared and gamma here by SC plus something again function of Mach number F1, better FC, Fm, and also of course of gamma as M, and also Fe M squared gamma as we have an expression of this kind just by substitution. So for the first term, for instance, this is gamma over gamma minus 1 by gamma minus 1 M squared over M squared minus 1 minus, so this is gamma minus 1 dt over t, and then we have dp over p, that is gamma M squared over M squared minus 1. So this is, for instance, the first step, and similarly for the other terms. We can see here directly that this will be 0, and we can also rearrange different terms to have this expression as a function of the Mach number rearranged for the entropy. So if you rearrange the equations, the relations related to the Mach number that is in square brackets here, what you find is that we have 0 by C plus something which is minus gamma M squared as M. Let's put it in this way, and then we have plus gamma 1 plus gamma plus delta M squared over gamma minus 1 as E. So what you see here, you see that if we have only a source term as C, so if Sm and Se are equal to 0, we have an isentropic flow. There will be no changes of entropy. Whereas once you have some Sm or Se, you will have non-isentropic flow. So a condition to get isentropic flow will be Sm equal Se is equal to 0. So we have no friction, no heat work addition, and no differences in terms of velocity and temperature. in case we have mass addition or subtraction. This can be, so why could be important this change of entropy? We can translate it in a change of total pressure. That, of course, can be important in our applications because losing pressure means losing performance or, in general, additional costs of getting the desired pressure. So this there is a relation between pressure, temperature, and entropy that we have already seen here. Being the change from static quantities to total quantities, an isentropic change, this relation is also valid for the corresponding values of total quantities. So it will be the S or R will be gamma over gamma minus 1 dt0 over T0 minus dp0 over dp0 over p0. As a consequence, I can evaluate also our total pressure loss. That will be clearly gamma over gamma minus 1 dt0 T0 minus ds over R. Of course, our dt0 over T0 by definition is our SE. Is our SE, so we can just add here gamma over gamma minus 1 SE, and we obtain the result for the P0 over P0. So it will be minus gamma m squared Sm plus gamma over gamma minus 1 plus delta m squared. Sorry, we have this is positive, this is negative because we have a minus sign. And SE, and then we have plus gamma over gamma minus 1 dt0 over T0, which is gamma over gamma minus 1 SE. So you see that here these two terms, let's say this root 1 and this term here, will cancel with each other, and so we have that dp0 over p0 is this term for the momentum equation source term and a similar term for the energy equation source term. So this is because I have here gamma minus 1/2 divided by gamma minus 1, which will be 1/2. So at the end, we also realize this result for the total pressure loss, and we see that this will be appearing when we have a source term as M, when we have source term as E, and you see that positive values of this quantity, or better, negative values of this quantity or positive value of this other quantity will lead to total pressure losses that we will comment later. So, in fact, what we see here from this discussion, that we have also analyzed the role of total pressure and entropy, but also from what we were considering last Wednesday, we of course, have a different behavior that will depend on the Mach number and on the driving potentials. One interesting thing is that when we write the system of equation as P over P, the M over M, and the T over T, what we have on the right hand side will be something function of Mach number, something function of Mach number, some function of Mach number in general, and SC, SE, SM, SE. So if you now look at this second equation, you see that if we consider the source term as constant, we can, in principle, integrate the equation by separation of variables because I only as unknown the Mach number. And so we can try to see in special cases if I'm able to make this integration for assuming by separation of variables that will be able to tell us something depending on the different source terms here. 1, 2, and 3. So let us first go back to this equation for the Mach number, and let's write it explicitly. Okay, and with all source terms, again, you can take your notes or what you have already. You can find also on e-learning the notes, and you see that here we can write, we can group we have a common group which is 1 plus delta m squared over 1 minus m squared, and then we have different terms related to the different source terms. 1 alpha plus gamma m squared SE. So you see that changes of the Mach number are related, will be of different sign depending on the sign of this quantity here in the denominator and of the term that is comprised between these square brackets. So I will group this term with the symbol lambda. And you see that the sign of changes of the Mach number will depend on this lambda and on the fact that the flow is supersonic or subsonic. So it's interesting to study the sign of these changes. And we can consider the cases where we have this lambda greater than equal to or lower than less than 0. And we and different also Mach number 1 or less than 1 or greater than 1. So we can draw a matrix when we have here different values of Mach number, different signs, so of 1 minus m squared, and when we have also the sign of lambda. Sorry, this is less, equal, and greater than 0. So when the sign of lambda is negative, we have that if m is less than 1, we have that we have the same sign of lambda. So here, in general, if we have Mach number less than 1, we have the same sign as lambda. So here we have less than 0, greater than 0, and here we have the opposite sign. That means greater than 0 and less than 0. When lambda is equal to 0, we have that this is 0 here and here. Whereas when Mach number is equal to 1, we have that 0 is at the denominator. So we have, let's say, infinity here, and here we have the form 0 over 0. So we can say that we have similar conditions when lambda is less than 0 and m less than 1, or both positive. So if they are both positive or both negative. So we can identify something like this pair and also this other pair. So what we see, but there is also a different meaning that has to be underlined of the change of sign of the Mach number. Because if we are, let's say, in this regime, if we have Mach number which is less than 1, increases of Mach number can move us towards the singularity of m equal to 1. Whereas if we are in the supersonic regime, we have that we will approach Mach number equal to 1 if we have a decrease of the Mach number. So you see that we can also say that if you look to the first line where we have lambda less than 0, we are, let's say, moving away from m equal to 1, so it becomes farther and farther from there, whereas here we are approaching m equal to 1. So you see that from this point of view, the different behavior will be clearly depending on the sign of lambda, which plays a prominent role on the flow evolution. And in fact, so if we consider the first case, lambda less than 0, we are going away from Mach equal to 1. If I consider, for instance, Mach number as a function of x and constant lambda less than 0, what happens is that if this is Mach number equal to 1, we can consider a starting point like this, and what happens is that I will be moving towards Mach number here supersonic, but greater than the initial value, because we are increasing, you see here, this change, positive change. If you are considering Mach number less than 1, you further decrease your Mach number because we have less than 0 here, and we move in this direction. And so we can consider different curves of this kind starting from different Mach number. And what you see that we have no problem, we always have solutions for this case. Different is the case with lambda greater than 0. We still consider this value of lambda constant. You see the Mach number here as a function of x. So what happens here is that if you start from supersonic value, you will decrease your Mach number. And at a point, if the channel is long enough, you will reach Mach number equal to 1. And that's all, you cannot go further. And similarly, if you are in the subsonic regime, there will be something like this. You will increase your Mach number up to 1. And what happens once I am here? If I look to governing equation, we can assume, for instance, let's consider that the next step will be a value lower than 1. We are considering this line. So we pass from supersonic flow, we reach Mach number equal to 1. And then we are considering now that what happens. Let's consider what happens if we have downstream a value of Mach number less than 1 or greater than 1. If this is less than 1, it means that we are in subsonic regime and lambda is greater than 0. So the flow will react, bringing us towards higher Mach number. So we assume that we are decreasing Mach number, but the system would react as increasing. So this is not possible. And the opposite will occur if you assume that Mach number will increase. Of course, the governing equation will say that Mach number should be should decrease. So again, should be no different from 1. So this is what you know as the phenomenon that is referred to as choking, and that you see that is the result of the assumption that we make here in these schematics, that we can take for a given channel, a given one-dimensional flow, we can take any initial condition. So this is not real case, because in the real case the flow is governed by the upstream and downstream environments for that channel. So actually it means that these initial conditions are not allowable if I'm considering a channel with this length here and this value of lambda. So you can imagine this, and we will discuss then later for the nozzle, but you can imagine that we cannot fill with any mass flow rate the channel. If you try to put inside more than allowable, you will have something that is not possible. So there will be some mass flow rate that will not be able to enter your channel. So there will be a shock if you are considering supersonic flow, and there will be some, let's say, bleed of the flow outside of the channel if you are considering subsonic conditions, and the inlet Mach number will adjust, for instance, to this value here or to this value here to get Mach number 1 at the exit. An interesting case is related to the fact that lambda in principle can change. We have considered the terms related to friction that doesn't seem to change. We cannot control so much, but some control is still possible with, for instance, with roughness. And we have considered heat flux, or let's say heating in general, more than heat flux, and we can manage heating or cooling, mass addition or subtraction, and also area change that can be positive or negative. So in general, we can consider that lambda changes, and we can also consider a special case where it also changes sign. And so we can see, for instance, a case where we have, let's say, let's put here an axis for lambda, and let's consider the case where we have lambda evolving in this way, and we have this line which is mark equal to 1 and lambda equal to 0. So if you start from here, it happens that on this side we have lambda less than 0, and on this side lambda greater than 0. So if you have lambda less than 0, you have this increasing up to here, and then we start decreasing, and similarly. And the same will occur on the subsonic part. So nothing special, except that the fact that you have to keep in mind that once we reached the condition with lambda positive, you can be in, let's say, in the conditions that can lead, for instance, here to choking. On the other hand, if you consider now the case where we have similar plot of lambda m, this line with 1 and 0, and we consider the different behavior of lambda now decreasing, so that we have that here is lambda greater than 0 and here lambda less than 0. Of course, if you start from here, for instance, you have something like this, and the story ends soon. Similarly from here, but it may happen that we have here lambda is equal to 0, and you can reach this condition at Mach equal to 1. And so in this case, what happens is that now you can start both solutions from this point m equal to 1, so solution A and B. And this can also be true if you reach this point from this side, so from the supersonic side. So we see that we have at lambda equal to 0 a possible bifurcation that allow us to pass from supersonic to subsonic and vice versa. Well, this is known for converging diverging nozzles for if the driving potential is the area change, and we have to consider here trot where is dA equal to 0. So it's lambda equal to 0 too, but in general this is true in different position and also due to other phenomena like friction and heat exchange, so increase of the total temperature or decrease of total temperature. So in principle we have different conditions that lead to this choking. So I think we can stop here for the first part of today's class, and we will now have 15 minutes break that we will resume at 1:15. Or sorry, change 10 minutes. We say that we should finish 5 minutes before, so the agreement was up to 1:10. So after this general review of the generic flow, one-dimensional flow with different driving potential, we go back now to specialize these equations to cases where we have a single driving potential at time. So we start from the well-known case of area change. And here we have to go back to our source terms, considering that the driving potentials are dA, the friction, and then we have the dot m and dt0. So we have, in this case, we are going to consider the assumption that this can be in general different, it can be not zero, whereas all these other terms are assumed to be zero. As a consequence, we have that our SC is minus dA over A, as m is equal to 0, SE also. The system of governing equation will be therefore only consider the first column of the right-hand side where we have a C. So it will be dP over P equal to minus gamma m squared over m squared minus 1 dA over A. dm over m is 1 plus delta m squared minus 1 dA over A. And finally, dt over t is minus 2 delta m squared minus 1 dA over A. So we have, let's say, a simplified system of governing equations. And based on what we have seen a few minutes ago, when as m is equal to 0 and the c is equal to 0, the flow is also isentropic. And we know that this is equivalent also to say that our change of total pressure is 0. Being as E equal to 0 is also T0 is equal to 0. Finally, we have also underlined that an important role is played by our lambda. And we record that lambda is related to SC minus gamma m squared as m plus 1 plus gamma m squared as E. And so in this case, it's minus dA over A. Just something come to my mind, something that I didn't say about our lambda. I go back for a minute. So if you see here, this is the expression of lambda. And if you put here m is equal to 1, and you compare with the conditions to have solutions in case of Mach number equal to 1, you see that this is exactly the results of that we had for the linear combination. So on the right hand side should be SC minus gamma SM plus 1 plus gamma SE equal to 0. That corresponds to lambda equal to 0. So lambda equal to 0 with Mach number equal to 1 means that the equation is a linear combination of the other things are related with each other. So sorry for this interruption. And let's go back to the flow with area change. And here our lambda as this expression. So we see that we have lambda less than 0 when dA greater than 0, lambda greater than 0 when dA greater than 0, less than 0, and also that lambda is equal to 0 at Mach equal 1 if dA is equal to 0. So we have this as the condition for bifurcation. We have this as the condition for choking. So we can have choking if we have converging channels with dA less than 0. And we can have bifurcation if we have a change of sign of the area change. So of course the choking condition will occur in a converging channel if we, in case of both hypersonic or supersonic or subsonic flow. In the first case of supersonic flow, we have Mach number decreases up to 1, and the second case, the subsonic flow in a convergent channel, will have Mach number increasing up to 1. We can also see that here we can make the integration of the second equation of Mach number. We can do the integration by separation of variables, and we can say that between points 1 and 2 of dA over A, I separate variables and I say that this should be equal to the integral between point 1 and 2 of m squared minus 1 over 1 plus delta m squared dm over m. So I can reduce it in a way that I can integrate as a function of the Mach number, and the way of doing this is the following. First we make appear only m squared, and then we see that this m squared minus 1 over 1 plus delta m squared multiplied by m squared can be expressed as the sum of two contributions. Let's say C1 over m squared plus C2 1 plus delta m squared. So we can determine if this can be expressed as the sum of two contributions, then I can make the integration for the first term and the second term, and I can do it because it will be something like dm over dx over x. So we can compare the resulting numerator coming from considering the common denominator here with m squared and 1 plus delta m squared. It will be a function of there will be c1 plus c1 delta m squared plus c2 m squared, and this must be equal to m squared minus 1. So making the equivalence of the zero order term and of the m squared term, we obtain that C1 is equal to minus 1 and C2 is 1 plus delta. And as a result, the integration will be the integral between 1 and 2 of dA over A equal to 1/2 1 to 1 plus delta over 1 plus delta m squared dm squared minus 1/2 1 to 1 over m squared dm squared. And so you see that this is also it can be expressed as d1 plus delta m squared over delta. And so we can obtain the integration that will be all logarithms. So in particular it will be logarithm of a2 over a1, then is equal to 1 plus delta over 2 delta logarithm of 1 plus delta m squared 2 and 1 plus delta m squared m1 squared, and finally minus 1/2 logarithm of m2 squared and m1 squared. Solving for this, or better exploiting the properties of logarithm and obtain the relation between a2, a1 and the two values of Mach number, is something very well known. a2 over a1 is equal to m1 over m2, 1 plus delta m2 squared, 1 plus delta m1 squared, gamma plus 1 twice gamma minus 1. Of course, always exploiting these two symbols, gamma and delta, which are related with each other. And this is the laws of the areas that can be, as we know that there will be minimum area that can be reached in converging, starting from a point and reducing the area. We can have a limiting condition, which is the one of choking. So we can refer the generic area A to the critical area A star, and which is obtained when m is equal to 1, and express this relation in this way. That in turn can be plotted in let's say we can plot A over A star as a function of Mach number and identify a 1, 1 point. And we see that we have something like this that tell us that the allowable area ratio that can be considered should be such that, let's say, you should keep in mind that we will reach critical condition along this line. So at this point, if I have, for instance, a subsonic flow, I know that if the initial area is lower than this one, that will be choking. So all the solution will be here above. This is possible solutions, and here will be impossible. So we have no solutions with starting from an area less than, let's say, the ratio to the critical one. So just a warning about what is usually known about this law is that you are probably used in considering this equation for air, gamma 1.4. For all the propulsion applications, or better rocket applications for sure, this gamma is never 1.4, especially if I'm considering chemical rockets. It will be 1.2, 1.15, 1.25. This will be the range, and but can be different depending on the kind of propellants I'm considering, and also the temperature in principle, because this is also the other warning, is that we are now talking always about calorically perfect gases, which is not the case typically in rocket engines. So be careful in using tables about this law. Often tables are related to, or better, tables are obtained with a given value of gamma. So if value of gamma is not available in that table, you cannot exploit tables for the computation. Next case, flows, 1D flows with friction. Well, this is slightly less familiar. So again, we have dA, dF, d dot m, d T0, Q minus W. And in this case, we assume that dF is not 0. So again, one driving potential time. And in this case, big d dot m equal to 0, there will be not the contribution which is present in all equations by this driving potential. And so we see that actually in this case we will have SC is equal to 0 and SM not. More specifically, it will be SM is equal to minus dF over rho u squared A, where A is the area of the cross section. That will be constant because we have no area change. So to better express and analyze this case, it's convenient to recall the way we used to express this stress, let's say this friction force. We use typically the friction stress, let's call it tau, which is a force per unit surface, and we express this through the dynamic pressure, 1/2 rho u squared, and skin friction coefficient CF. So this is the friction force per unit area, and the overall friction force will be given by, this is a positive quantity, assume it as positive, so this dF is also a positive quantity, and this will be tau by the wet surface, that for a length dx will be the perimeter of the cross section by dx. So this will be the perimeter. So with these definitions, if you consider now the term dF over rho u squared A, it becomes 1/2 rho u squared CF. This is tau P dx and rho u squared A. That is this cancel, and so is 1/2 CF P over A dx. If you have a special case of circular cross section, you have that P is pi d, and d is the diameter, and A is pi d squared 4. So it becomes here 1/2 CF. I simplify pi, so I have 4d over d squared dx. So at the end we have that for circular section channels, I have here 1/2 4 times CF and dx over d, which is a non-dimensional length. So because of this relation, in case of channels, we introduce hydraulic diameter, which is defined exactly such that this expression holds also for channels without hydraulic, circular cross section. So we define this dH as for A over P, and we define under C friction factor, which is 4 times Cf. And this one is the one you find on the Moody diagram. It's a function of the Reynolds number and of the relative roughness. Or you can find formulas like Colebrook formula for the expression of this F as a function of Reynolds number and relative roughness. So at the end, we have that our SM is minus 1/2 F dx over T. And we can now consider the equations with this driving potential. It will be dP over P gamma m squared 1 plus 2 delta m squared, taken from the Euro system before, but only with the second column where we have Sm, which is the only S which is not 0. And so the same equation, so the similar equation for the Mach number and for the temperature, minus gamma m squared 1 plus delta m squared over m squared minus 1 2 gamma delta m4 m squared minus 1 1/2 f dx over d 1/2 f dx over d. We can have a look also to entropy and total pressure equations that clearly yield ds over r will be equal, in this case, gamma m squared 1/2 f dx over d, and if it's 0 over p0, similarly minus gamma m squared 1/2 f dx over d. We have SE is equal to 0, and so also that is 0. So you see that here we have not an isentropic flow. We do have changes of entropy. This is positive, the X is positive by definition, as a consequence also the S is positive, and it's clear that dP0 is negative. So we have a non-isentropic flow because there are currents related to the different momentum. We have our wall, which is 0, and within the core flow. So because of friction at wall, we have these currents, and we have a flow which is not isentropic. The flow is adiabatic by assumption, and we have a decrease of total pressure as shown here. So we lose the possibility, some possibility to make work because of friction that converts the available energy in unusable energy. So from, let's say, well organized internal energy towards something which is less organized because of friction of random motion. So finally, we have to recall that we have an important quantity, which is our lambda, and our lambda is here gamma m squared 1/2 f dx over d. Just substitution with the present assumption. So what you see here is that lambda is always greater than 0. So we don't have the opportunity to have lambda negative or positive. It's always greater than 0. That means that the flow will behave like if it were in a convergent channel. So it can choke. It can reach choking conditions. It's similar to dA less than 0. And this can be also, of course, let's say, to keep it in mind, we can imagine that the result of this friction is like if we have some thickness at wall that makes the channel similar to a converging channel. Okay, so this is the governing equation. Also here we can work similarly to what we have done for the area change and focus on the equation for the Mach number and see if we can make integration by separation of variables. That will be, in this case, now, well, this is the equation, and we can write it f dx over t is equal to minus m squared minus 1 gamma m squared 1 plus delta m squared the m squared over m squared. So just putting, just considering the separation of variables and changing the m over m in the m squared over m squared. Well, we can make the integration. Let's just have to consider here 1, 2, and 1, 2. And we can proceed similarly, splitting the integrand here of dm squared in two terms, considering the two factors that we have a denominator. And I will not consider now so we have here, actually we have to consider gamma m4 and 1 plus delta m squared, but we can proceed similarly. We have just to consider also m squared and numerator for the term that where we have m4 to denominator. So I'd like to skip this and move to the integration. If f and d are constant, d is constant by definition because we have dA equal to 0. F we assume now also that it is constant, so that we have f over d x2 minus x1 will be equal to so skipping passages, it will be 1 over gamma 1, 2, 1 plus delta m squared minus 1 m4 dm squared, and then we have 1 plus delta 1 plus delta m squared dm squared. So we have split this integral in two parts. At this point we can consider three integrals on the right hand side. One is in the first term of this integral we have a function of kind dm squared over m squared, and on the second term we have dm squared over m4. So in the first case we have something like dx over x, and in the second case we have something like dx over x squared that we are able to integrate. And on the second integral we have here something like dx over x. So it means something like a logarithm as the integral. So at the end I can bring this gamma on the left hand side and say that gamma f over d x1 minus x2 is equal to 1 plus delta ln m squared 2 and 1 and plus 1 m2 squared minus 1 m2 m1 squared minus 1 plus delta and the logarithm of 1 plus delta m2 squared 1 plus delta m1 squared. So you see that we can have this integration, and we can also compact different terms within the logarithmic expression. And so I will write this in this way. First, I consider the term without logarithm, and then a single term within our logarithm sign. That would be m2 squared 1 plus delta, because you see that both terms are multiplied by 1 plus delta here, so you see they have the same exponent within the logarithm sign. This is 1. They have, this is one term is 1, another is minus, so we have exchanged numerator and denominator 1 and 2, and this will be 1 plus delta. Let's put this inside so that it's clearer. So from this expression, what can be done is that if we start from a condition with a given value of Mach number m1, and we know our constant gamma and d and f, we see that to reach a given value m2, we can put m2 inside this expression, and we obtain the corresponding length of the channel needed to reach this Mach number. Or you can, of course, you cannot invert directly, but you can see that for a given length and initial condition m1, you will have a given value of resulting m2. This would be possible provided that we don't reach the choking condition. So we can identify the choking condition as the one such that m2 is equal to 1. So we can say here minus gamma f over d, and we'll consider length. Let's say at critical length L star, it would be 1 minus 1 over m squared plus our logarithm that must be expressed for m2 equal to 1. And so we can plot this condition and see that our length cannot be greater than the one allowed by choking. This is f L star over d. This is the Mach number. You have 1, and here you have 0. So the length will be, allowed length will be 0 if you start from Mach number 1. If you are in the supersonic or subsonic regime, for instance, here you can have all the lengths which are less than the critical one. So we have no solution here. Note that this would be reach an asymptotic value in case of a high value of m, and this asymptotic value will depend on gamma, and you can see it's between 0.8 and 2 for ranges of gamma between 1.1 and 1.4. Of course, you can rearrange. Once you have this kind of expression, you can also you have relations between the ratio of different quantities and the ratio of Mach numbers, or let's say expressions where appear the two different Mach numbers. So you can rearrange and obtain also other expressions. For instance, here being T01 equal to T02, because you have constant total pressure, you would have that T2 over T1 is equal to 1 plus delta M1 squared over 1 plus delta M2 squared. And similarly, you can also obtain, or not obtain it here, a relation between P02 and P01, and this will be M1 over M2, 1 plus delta M2 squared, 1 plus delta M1 squared, gamma plus 1 over 2 gamma minus 1, which is formally the same expression that we have for the A2 over A1 in the case of only area change. P02 over P01 is the same expression for the flow where we have only friction. So this is just to say that possibly you can recall it more easily. The behavior that we have of the flow with friction that we have analyzed here, starting from the governing differential equation, is also seen in terms of the integrated values. And in particular, it's of interest to see the locus of point followed by a flow with friction in a temperature entropy or enthalpy entropy diagram. Let's consider this, our TS diagram, and that we have a given point on this diagram, which is our inlet conditions, our value 1. So we should identify what is the locus of the points of the channel downstream of 1. To do that, in this diagram, of course, we have to relate the behavior of temperature and entropy under the condition of the flow where the only driving potential is friction. And this will be called as the Funnel flow. In this condition, we have that our total temperature is constant. Of course, it's also true that .m is constant, and being A equal to constant, it also results that .m over A, which is the mass flux, or G, is equal to rho U is constant. This is G. So we can exploit the relation that we have seen. Let me go back here. So if you like to relate the temperature and the entropy, you should look to this equation here and this equation here. You see that we can cancel our 1/2 f dx over d, which can be seen in both equations, and relate the one with the other. The result will be this equation, ds over r is gamma m squared, m squared minus 1 over 2 gamma delta m squared that multiplies dt over t. And that simplified becomes m squared minus 1 over 2. We can simplify gamma m squared. Here it was m4 here, sorry. And we obtain that is 2 delta m squared dt over t. And so we can just rearrange this expression, also exploiting the fact that we have T0 is T 1 plus delta m squared. We exploit this, and we so that we can also eliminate the Mach number. And we see, because here we also write well, I can say that ds over r is 1 over 2 delta minus 1 2 delta m squared dt over t, and take delta m squared from here. So at the end, we will have that this is 1 over gamma minus 1 T0 minus 1 plus delta t over T0 minus t by dt over t. So this help us to see what happens on this plane. In particular, we know that we have that T0 is always greater than t, so the denominator here is always positive, whereas the numerator can change sign no, it doesn't change sign. Sorry, it can change sign depending on the value of t, because we have 1 plus delta. And so what we have is that the sign depends on the fact that T0 is greater than, less, or equal of t, delta plus 1 t. And what is the meaning? The meaning is that this is equivalent, we recall this equation here above, and we see that T0 is equal to t by 1 plus delta when m is equal to 1. So this corresponds to, say, Mach number greater than, equal, or less than 1. So it means that when we have m equal to 1, this is 0, then we have the ds equal to 0, and it means that in practice we have reached our point at Mach 1, where we have ds equal to 0. If we see the behavior of entropy as a function of temperature, we have a maximum. And we can find at this point a line like this on this plane. So this is given for given amount of flow rate for a given G, and we have given value of T0 here. And clearly we have a higher difference between the total temperature and the static temperature on the top branch, that would be for Mach number less than 1, and a higher difference for the supersonic branch. In both cases, here we can see that we move towards the value of maximum entropy, which occurs here when Mach number is equal to 1. And these lines are used to compare different conditions in special cases of flows, and with lines that can be shown for different values of G, and it can be shown that we have lines of this kind that corresponds to different increasing value of G in this direction. Because if you consider that G is also given by its critical value, this is rho, and this is the velocity, you can rearrange this and see that for a given T0, we have that G is proportional to P0 critical. And so you see that here G is increased if P0 increases. That is the same to say that G increases as entropy decreases. So we stop here for today, and tomorrow we will also comment about heat addition and mass addition, and I will start with the detail of flow in nozzles.